Let's look at an example of a 2D equivalent force system. So we have this system here with origin up, or this point O up here, and 8 feet 6 inches to the right of it, there's a 300-pound force, and then another 11 feet 6 inches, we have a 500-pound force acting down. And then down here in the bottom right-hand corner, which is 2 feet below the 500-pound force, there is a 200-pound force acting to the bottom right on a 3, 4, 5 force triangle. And what we want to do is simplify this down into one vector. We don't want to draw 3 of them. We want to draw 1. And since this is a 2D system, this fit that second definition of when you can do this, right? When all the forces are coplanar. So the first thing we want to do, find that resultant force. Since we have non-parallel forces, we're going to need to do X and Y for this. Then we'll calculate the moment due to each of those forces, and we're going to do moments about O. Then we'll calculate the distance to the right of O such that no additional moment vector is needed. Okay, so really, when you want to find the one place that it's going to be applied, normally what you want to do is think of one reference point. And so here we have this point O. So what you're going to do is say, well, let's calculate this FR, find some value for it, and then say, okay, well, let's move it over to O. And when you move it from all these places over here over to O, you're losing the moment those forces generated. So you have to calculate those moments, like the 300 pounds times it's 8 feet 6, and the 500 pounds times the, 20 feet. And this one here also is generating moment. Both components are generating moment. And so you calculate what the moment about O is due to all of these, and then you say, okay, well, if I move the vector away from O, it'll start getting moment caused about O by my new F sub R. As I move it away, the moment's going to get greater and greater, and I just need to move it just the right amount so that it balances, and it makes it where no additional drawing of a moment vector is needed. So when I do these, I usually end up calculating the moment and even drawing it oftentimes on my diagram so that I see it. So we'll basically do where we simplify this into a force and couple system and then simplify it one more time into just a single force system. So let's find that resultant force, F sub R. So in the X direction, we only have this one that does anything in the X. The X is going to the right. I'm not really showing it. So this is a force triangle with the horizontal line here being the 4. So I have 4/5 of 200 for my X component, and that's 160 pounds to the right. My Y direction, I've got 300, 500, and then 3/5 of 200. And they're all acting down, so I'm saying negative. So I have the minus 3/5 of 200, minus 500, minus 300. I get minus 920, or 920 pounds acting downward. So then my F sub R would be the square root of the sum of the squares of those, right? Because those are my two components of my resultant force, my X component, my Y component. So I just do the square root of the sum of the squares, and I get 933.8 pounds. Okay, that's the magnitude of it. It's not acting vertical or horizontal. It's acting at some weird angle, and we need to figure that out. And you know how to do this. We've done this in previous lessons. We just solve for the orientation. Here I've got the arc tangent of minus 920 pounds over 160 pounds gives me minus 80.1 degrees. The angle is swinging down clockwise 80.1 degrees from the positive x-axis. Let's calculate the moment. So we'll just hold on to that 933.8 for now. We'll calculate the moment due to the forces that are applied. And we're going to use counterclockwise positive here. And I'm doing that because I've taught you that moments are usually assumed positive when they are counterclockwise. So we're going to stick with the sign convention. You could say, okay, well, for just this exercise, I'm assuming clockwise is positive because all the forces are pointing that way. Pretty much there's only one that's going to be one moment that's going to be counterclockwise, and that's going to be the X component of this 200 pounds. But we're going to stick to the main sign convention for now. So here I have 300 pounds times 8 feet 6 inches, which is 8.5 feet. And then I have 500 pounds times 20 feet. And they're both negative because they're both clockwise moments about O. as is the vertical component of the 200 pounds. So minus 120 pounds times 20 feet, because it's also acting at 20 feet. And then I've got the x component acting down here at 2 feet. Keep in mind that x component is really right there. And so that's causing a counterclockwise moment about O, right? And so this one will be positive. So it's plus 160 pounds times 2 feet. You do all that math and you get minus 14,630 foot-pounds, or 14,630 foot-pounds clockwise. So if you notice how I write this, this is how I like to write it if I'm writing it by hand or on PowerPoint. I like to give the answer with its appropriate sign based on my equation up here. And then if I decide to think about it as just a magnitude and a direction listed separately, I'll then say comma or 14,630 clockwise. Right? So that way I don't write like minus 14,630 clockwise, because then you're like, wait, is it clockwise or is it counterclockwise? Because now you got a negative of a negative in a way, right? So I like to be clear on how I'm writing this to myself. So that's what the system would look like simplified down to a force and a couple moment at O. So we've got the 933.8, which is F sub R. It's acting at 80.1 degrees. I actually calculated it to be 80.13 from the horizontal, acting down at O. This 933.8 pounds does not cause a moment about O. So I have to add this moment to account for the moment that I lost when I moved all those forces and combined them into this 933.8. This isn't the final answer because we want it down one more step. We want to get rid of this moment vector. We want to not show it. Well, what we're going to have to do then is move this vector over. And the question said to the right of O. So I'm going to slide this to the right across the top of this beam here at O, which means I'm moving it purely in the X direction. Okay, that's going to have an impact on me when I go to calculate what the moment impact is of this 933.8. If I'm moving it in the X direction, then the X component of this 933.8 will be acting through O. It will generate no moment about O, the X component, the smaller part, but the Y component will. You'll see that here. Now, let's calculate the distance to the right of O such that no additional moment vector is needed. So like I said, we are going to move it directly to the right along the x-axis, so no moment will be generated by the x component. So the moment would have been Fy times d plus f sub x times whatever distance it is, but it's not going to have any distance because it's sliding along the top of this beam. So the perpendicular distance to the x component will be 0. So this just goes away. So I know my moment is 14,630 clockwise. As I'm moving the force to the right, it's going to be causing a clockwise moment. Okay, so I've just kind of dropped that negative sign because I know that at this point that it's going to be causing a clockwise moment with this 14,630. And so I'm good. I'll take 14,630 foot-pounds and divide it by the y component of the resultant, because that's the only part that will be generating moment, and I'll get 15.9 feet. Now, if you're like, I really don't know what you're talking about there with your negative signs and dropping them, that you could keep them, okay? Follow your sign convention to the T. Counterclockwise positive, down negative, you'd have minus 14,630 foot-pounds here, and then you would have minus 920, and you'd end up getting 15.9. So this is what the beam would look like. This here is equivalent to this. As far as the moments and the forces acting at O, it is identical. The point O sees no difference between these two. 933.8 acting at an 80.13 degree angle from the horizontal, and then slid over 15.9 feet in the X direction. And, you know, it's really easy to double check your work to make sure you did it right. You just run all the calculations the other way. Just calculate your moments and forces about O. So find your X and Y components of this. They should match the X and Y components of that. Calculate your moment about O based on this. And it should match the moment generated by your original problem. As long as all those match, you did it right.